All right, so it's Tuesday, May 4th, class number 14, Pkt6. We'll get a little gold standard today. We'll do some angles in the free body diagrams, some of the nuts and bolts of that. Oh, before we get on to the next one, let's see what else we got going on here. Books. I gotta put some books on the front porch for you, but I know a lot of you don't come by the front porch anymore. We were talking about in class a while, kind of last week, we were talking about Voyager and it's sending signals back from, it's out beyond Pluto now. It's out there in the Kuiper Belt, sending signals back to us, back to JPL. And so the question was, how long would it take it to send that signal back? And so I started looking it up and I found this graphic. The moon, as we know, is the closest. It's about 1.3 seconds. So when you're talking to somebody on the moon, there's a good chance you'll talk to your grandkids, right? It's be about 1.3 seconds one-way trip. And so that's a light wave, which is basically is electromagnetic wave, which is like the signal you're going to get. So it takes, so put that together, 2.6, about 3 seconds. So when they're on the moon, you'll be talking to them. Say you actually talk to them, say hello, and then you got to wait about 3 seconds for them to say hello back. So it's a delay, not that bad. Mars, they showed the delay there for having a conversation would be 4.35 light minutes. Light minutes being how far light travels in 4.3 minutes. That seems short to me. So I looked it up, and for Earth to Mars, we come as close as just 3 minutes right here, 3 minutes and 13 seconds. That's when we're like this. If that's the sun, sun's the yellow, Earth's blue, Mars is red, that would be when we're kind of lined up. That's the shortest time. So we could do it in 3 minutes and something. But then if this is the sun here on the furthest it could be, Mars from us, say that's the sun, and then Mars is on one side of the sun, we're on the other, that would be about 22 minutes. So it's going to vary. So I think you're going to have to time it. If you really want to hear their voice and not just the recording, you actually want to try and communicate, you got to be patient because now we're talking, 6 minutes at the best for Mars. So say hello, go out, do some gardening, come back in, and then wait for them to say hello back. But otherwise, it's 45 minutes before they return your hello. Or Zooming. Zooming would be, you have to do it in chunks. I'd have to, if I'm teaching you and you're on Mars and I'm teaching you from Earth, I'd have to, depending on the time of year. I think we'll get to know pretty well the patterns of where Mars is as opposed to Earth in the next 100 years. We'll have to kind of know to know what the signal delay is. So pretty much you'll be texting, right? That's Mars. Jupiter's about 35 minutes. Saturn's about over an hour to get to to get a signal to Saturn, Uranus. You get to Pluto, it's about 4.5 hours away. I think 5 hours now is the answer to the question, how long does it take Voyager to send a signal back? So say Voyager takes some data, takes a picture, it'd be a very low res picture, but takes a picture, sends it back. It's going to take about 5 hours to get back to us, even moving at the speed of light. So I keep saying Voyager because that's the furthest man has put an object out into space. I remember I was telling you yesterday that I was giving my kids the dates of all the AP tests. Well, I was off because that's paper and pencil tests. So now I guess the only reason I care about it is I want to know when my class is going to be half empty. And apparently now there's 3 ways to administer the test. One's paper pencil, the old fashioned way, which I think Norman Public Schools is not going to do. I guess they were so happy with the success of the SAT through the internet, cough, cough, that they decided that that's the way to do AP. But to me, you're asking for problems, but that's just me. So anyway, AP tests, I'm the last person at Norman High to know this, is now you can take it at home. I guess you can take it online at school. So the point is that it's just forget trying to figure out who's going to be who when. So I'm just going to ignore it and assume we're all there every day. We're here in this thing. Okay, last thing before we get into the physics. This is the top 14 students in my class. That includes virtual, it includes all my sections. This is their percentages. So, I have probably 20 students that are playing above the rim that are over 100% in class. And the point I'm trying to make here is this was the practice problems, which I graded last night. And that's out of 0 points because it's optional, right? I make it optional just to kind of see who'll do it. But you could have got up to 42 bonus points if you did them all. I didn't really go back and check these seconds you're right, but I'm assuming you watched the help video. So look at these people that are in my top 14. Some of you are in this group. And look, see, they're hard workers, right? But they could just kind of rest on their laurels and by fumes just kind of get to the end of the year and still probably keep an A, but they're not that kind of people. They're going to take advantage of everything they have. Okay, now let's look at the bottom 14 scores. And unfortunately, there are people that are, I don't know if it's any of you, but there are virtual students that are in the bottom 14. I have hope for every one of these people. I think they can all still pass. But here's the cutoff right now. I talked to a couple of people today, and they're going to do some stuff tonight to get these 3 people can easily pass if they'll just do a few things. But what I want to point out is this is that same assignment from the practice problems, right? All that bonus. And look at this. And the thing is, there was a key. There's help videos for every one of those. You can do a few of them, do 10 of them, do something, but just the fact that I'm not saying you, but the fact that they didn't do anything to get them above the hump. I mean, don't complain that you're failing when you don't take what's given to you. It does my soapbox today, kind of let's do better and trying to keep it encouraging that we could do better. You can, if you find yourself in this group, there are things you can do. You can turn in any old assignment that you have a 0 on and get up to a 70%. If you have a 50% on old assignments, you can redo it and turn it back in for another 20%. You can get up to 70% for old assignments. Anywho, so, do not give up. Chess games coming along. Went around the room, gave stamps for 641. And they asked me, okay, I'll put a note here. They asked me if I'd post the key. So I will post the key to this tonight. Post key to 641. So hopefully you're keeping up. 6-4, we're going to kind of work on off and on. Like we're not going to work on it tonight, but I'll post the key to this number 1. All right. We're up to 9. Okay. We are going to meet table 4, but then couldn't redo it first hour, so we're going to push it back to Thursday. So I will meet one of you on Thursday. Okay, now on to today's physics. Okay, so we finished yesterday with looking at 3B on 6.3 and talked about these Newton third law pairs. There's the NB and the NA is a third law pair. The NC and the NB. So between two bodies, there's always that, especially if they're connected in some way. There's always a force on one, force on the other. Even the Earth moon is connected through gravity. So you don't have to necessarily be touching. You have a field force. A proton and an electron is connected by electromagnetic force. Okay, so, but in this case, mechanics, normally they are connected. All right, so we have normal force and they are equal and opposite. That's a Newton's third law pair. But then we said, if you take that green line and or green curve, put a circle around the whole thing, this is what Newton said. He said, then you can consider these 3 boxes as one body. And sometimes it's convenient AP tests, AP physics is famous for this, always having you, the only way to solve a problem is to combine bodies and to make them one body, then go back and separate them into other bodies. So that's a skill you have to know, is when to combine bodies and when to not. So like this whole set, A, B, C, may be sliding down a ramp. And at the same time, then you got to consider it all one body. But then they're asking, well, now box B starts to slide against box C, and then you have to separate them. So, but if it's convenient to make the whole thing one object, then what Newton said was then the NAs, the NB, the NC, those all become internal forces. And Newton said that all internal forces will kill each other. They'll all annihilate each other. So all internal forces cancel, is what Newton said. And we talked about this. All internal forces cancel. And this is all in the screenshots from yesterday. So he said, okay, if you make the entire universe an object, just make the whole thing one body, make the whole thing the ultimate system, right? The ultimate closed system is the entire universe. And this is Newton thinking in 1700, when we didn't even realize there's anything beyond the Milky Way. We barely even knew that. We thought they were stars up there. We didn't know those are other galaxies. No way. That wasn't until much later, till like the 1900s. So, and you couldn't see that far up there. So anyway, Newton said, okay, if I take everything, put a big, circle around everything, or a big balloon around everything, then all forces annihilate. There's no single force without its annihilator in our universe. Every force gets killed. Every force has an equal and opposite force. Okay? You can consider all forces internal if we make the whole universe the system. So right there, he anticipated the first law of thermodynamics, which basically says that all energy is conserved. So 1850s, James Joule and the boys comes along, and they do their paddle wheel experiment and all this, and they say, well, energy is conserved, voila. But then Newton already said that 150 years before that. Essentially, Newton didn't understand energy that well. I mean, give the guy a break. He's discovering lots of stuff, but he went on to become the, master of the mint and did other things. He got a little crazy from Mad Hatter's disease, and so started chasing criminals, but that's later on. So he really kind of got off physics later on in life. And then yesterday we were wrapping this problem up when we ran out of time. Here we go. So this was the homework. Hopefully you tried that. I'll post a key on that one. Let's hold off on the back till later on this week. But we were messing with this one, and we were looking at this. We said that Kr is rotational energy only for things that are rotating. So anytime something, a wheel, a baseball bat, anything, a hinge on a laptop, anything that rotates, by nature of it rotating, has rotational energy as opposed to linear energy. They have rotational energy. So there's something called the ultimate fighting tool, which you can attack any kind of mechanics problem with. And it has 9 components. 4 on one side, 5 on the other. But initial rotational energy versus final rotational energy. That's KRI and KRF are 2 of those 9 in the ultimate fighting tool. So a little introduction to it. We're not really expecting to know much about it yet. And so we did this stuff yesterday, and that's where we ended it. So let's go ahead and in class, we work this one together. So let's go ahead and work this together. Okay, here we go. So 2, I'm recording this, thank goodness. Okay, 2, 1, and this is KR is 320, which is huge, 320,000 newtons over a centimeter. Woo! That's a lot. That is a lot of energy compacted. So this must be a high potency motor. The moment of inertia, remember we said I represents how the mass is distributed. And I gave you a few examples. If all the mass is on the end, it's mr squared, like in a hula hoop. That's mr squared, but usually the mass is somewhat distributed from the axis of rotation out to that outside point. So it could be 2/5 mr squared, 1/3 mr squared, all those are ml squared, all those are in there. Anywho, you end up with a number. So the number here for this particular motor is 45, it's 1 over that, 45 kilogram dot centimeter squared. Okay, and those are the units of moments of inertia. So, aha, we catch a break. Bring out the green kill pin before I even start. Centimeters, one of those goes away. Now we got to end up in revolutions per minute, RPMs. And that's surprising. RPM per minute? I don't see any time in there. There's no time. What? There's no seconds, no hours, no days. What?
It's in the newtons.
Ah, it's hidden in a suitcase. So when in doubt, especially on a unit analysis, you have to open up those suitcases. So before I do that, I'm going to go ahead and get that kilonewtons out of there. Let's go ahead and let's go purple. So let's get the kilonewtons out of there. A kilonewton, turn them into newtons. That's 1,000 newtons. Now I can open up that Newton bag. And so a Newton, F equals MA. So a Newton equals kilograms dot, as far as units go, meters per second squared. But I can't do it that way. Like I can't just put newtons down here and then put kilogram dot meter per second squared, because that violates a rule. It's illegal. You have a divided unit inside a cell. So we bring the second squared over here. This becomes Newton dot second squared equals kilogram dot meter. So now I can go Newton dot second squared is equivalent to a kilogram dot meter. Okay, now we're cooking. Now they can bring out that kill pin. Kilonewtons got wiped out there. Kilograms is there. Boom, 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 boom. Newtons is killed. Oh, I'm going to circle that second squared. Remember, it's a radical. So I want to end up in revolutions. Oh, no. Sorry. We're not going to circle it. We're not there yet. Sorry. I got excited. Okay, so that's still second squared. Okay. Anything else I can kill? Well, now it's your option, but I get that low-hanging fruit. I'm going to get rid of that centimeter. So 100 centimeters in a meter. It's easy. And now kill. Boom, baby. 4 units in one move. That's a good chess move. So now I'm down to what? Oh, I'm down to second squared. So we got to end up in minutes squared. So let's go ahead and do that. 60 seconds in a minute. Let me square it. 3,600 seconds squared in a minute squared. Don't use M for minutes. Because I think it's meters. Circle that now. I'm going to protect it, and I'm going to kill the squared. Boom, boom. Aha. But we got a problem. It says revolutions. Now, this is where students got stuck today. What do we do with revolutions? How do we get that? I'll open up the chat. I'm looking at one screen, so it's really crazy here. How do we get rid of it? How do we bring we're not bringing revolutions in, we're bringing revolutions squared in. So the revolution will be televised. No, the revolution will be squared in this case. What do we do?
It seems like you would need the omega to know, but we don't have that, so.
But
You know the radian. Well, radians.
we do know about radians and we do know about revolutions. So in one revolution, how many radians are there?
2 pi.
2 pi. So if I say, and the cool thing about introducing that, you're not introducing any units because radians beautifully have no units. Somebody's clever. Not me, but whoever thought this up. So I'm just going to square it because I got to square it. It's got to end up being just revolution. So I square that. That becomes 4 pi squared. This is why this is a really hard problem. I didn't expect you just to pull that out. 4 pi squared. And there, that's it. So I don't have the answer in the back, but whoa. The answer ends up being kind of weird. Well, it ends up being huge. It's what, 11,400 RPMs. What is a red line on a car? You know, on your TAC, what's your red line for most cars, an average car?
Mine is a 6,500.
Okay, mine's around 6,000. That's revolutions per minute of your engine, okay, turning. So you run your car, unless it's high performance, you run your car at 6,000 RPMs, you'll probably be in trouble if you keep that up. Say you're driving down the road in cruise control down the highway. Where is your RPMs normally?
Like 2,500.
At the most. Overdrive on my truck, it's about 2,000. Some cars spin a little faster, but 2,000. But then if you really rev your engine, when you get in your car today, rev it up a little bit, put it, and look and see. You go to low gear, especially, it's going to rev up. But 11,400 seemed crazy high to me. This is for a motor, right? So I thought that's going to wear that motor out. But then we looked it up in second hour, and for jets, for like 747s, those turbines turn at about 20,000 RPM. So this is not beyond the realm of, like, it's not crazy numbers. This is a big motor. And those turbines, if you look inside those turbines on these 747, 737, there's tons of blades that go way back. But that's why you put a bird in there, you run a bird through there, a big bird, it gets stuck, boom, then you got Captain Sully situation. So 20,000 RPMs is what would be a big jet. Okay. So let's leave 6.4 for a while. We'll come back to it maybe tomorrow, maybe Thursday. Okay, so here's your homework. Many groans in class today, but I'm assigning the entire front of 6.5 as homework. Now hold out, don't log off. You can go ahead and cuss me out all you want because I can't hear you. But hear me out. I don't want you, I really do not, people think I'm an ogre, but I really do not want you to spend more than 15 minutes on physics a night, unless you're studying for a test. Okay, then maybe hour, 2 hours, I don't know, but 15 minutes a night. So you go, I can't do the whole thing in front. No, I'm not asking you the whole front. You can skip this one. You can skip this one. You can do them if you want, and I'll give you some bonus, but a stamp, this is for them. Now, I know you're not doing stamps. I think your points are going to come in. You have to have it done, but you're probably going to turn in 6.4, tell you the truth, but that's not till later. Anyway, just keep up with them. They're doing a stamp at 1, a stamp for 2A, a stamp for 2B, a stamp for 2 stamps for 3. So that's 5 stamps they can get tomorrow, which is like 15 points. And you will get those tacked on back to 6-4. So the front, we're not going to do it together. I'll leave that up to you. Most of those you can do right now. But I want to go to the back. Okay. So number 4, a little girl pulls a 10-kilogram wagon with a force of 60 newtons. Now I sent them to the board on 4ABC. So we're going to put it on pause in a minute and have you do that one. I wrote this 15 years ago, this problem, and I was looking out the window, and our neighbor, this girl was like 5 years old. She's pulling her wagon with all her unicorns and stuff in there at 9 at night. And I'm going, what is going on? So anyway, so I wrote this. I couldn't find anybody. So I told her to go home because you shouldn't be out there at night. So in my frustration for the situation, I went on and wrote this problem. So, and then the other day, I'm up here working, and I look out there. She is. She's 20 years old now, and she's walking her dog. That reminded me. I guess she survived. So what I want you to do on 4A is give me a free body diagram. Do the old Newton's second law, right? F equals ma. You got to find fx now. Something a little slightly new on this one. And then we're going to find the acceleration. So we're solving for a. This is fx equals max. And then this is a sub x equals what? And then find the normal force for 4C. So, okay, I know we said there's friction, and there is friction, but if it don't tell you what the friction is, you have to assume it's that it's negligible friction. Okay, so I'm going to pause this. If you're watching the recording, pause it yourself and then try this one, and then we'll come back and talk about it. Recording.
More in-depth investigation is routinely done.
I should have been more clear. I was more trying to gear that toward as far as reporters and the public to.
So I don't know what that's all about. Sorry about that. Okay, so here we go. We're back on. Check your work here. Keep working if you're working there. I'll just kind of work along with you. So we have a mg down. We have an n up, and okay. So here is the x-axis, and now that comes up at an angle that's 60 newtons. We'll call that the force of pull. 60 newtons. Make this bigger. Okay. And then this mg is, we know the m is 10 kilograms. And there's no friction. We all know there's friction. We're just saying it's negligible. Okay, and that's all we know. Hey, did I ever tell you guys that force, when a force is at an angle, it is the hypotenuse of a right triangle. So I'm going to draw that right triangle, and I use my color code here. This will be my X, and I'll make that orange just for old time's sake. And I'll make this purple, I guess, my Y. And then why not color it in, eh? Coloring each day soothes the soul. That is 30 degrees. Whoops. 30 degrees. And I'm going to go and do the work right there on, I'm a big believer in just doing the work right there on the drawing. So 60 cosine 30, right? This is 52. I don't even need to see you. I don't need to see you write out 50 unless it's symbols, but we're doing numbers here. 52 newtons, and then this side just for funsies, sine of 30 is 1/2, so this is just 30 newtons. So I'll accept that for work. Believe it or not, that's fine. That's enough work for me as far as that goes. Okay, so we're supposed to solve for Fx. I just did. That is Fx. That's the force in the x direction. So you only take a component. You don't, she's not getting, if she wanted to be perfectly efficient, she would have pulled that handle at horizontally to the ground, but she pulls it at an angle. So she's only getting part of that 60 newtons. She's getting most of it. But part B, what's the acceleration? Okay, so F equals ma. So summation of force in the x equals max. We only have one force in the x. So therefore, 52, which is 60 cosine 30, 52 newtons equals 10 kilograms times ax. And so acceleration then is 5.2, which is quite a bit. She must be being chased by a dog or something. 5.2 meters per second squared. And then finally, what's a normal force? Now, I think I probably caught up with you guys. How do you find the normal force? It's not, by the way, it's not 98. I know on tests I get 98 on this. It's not 98. How do you do it? Strategies?
Well, you start with the 98 and then you subtract the 30 newtons from the
Okay.
y.
So what you're doing is you're just saying, I'm just going to look at the y now. So summation of force on the y is equal to may, but that wagon is not levitating, it's not sinking, so that's just zero. There's no motion in the y direction. So you're right. So now let's go to the y direction. And let's just establish this is important here. Let's just say that DOM on free body diagrams is always positive, and to the right. So that's fine. So normally you say direction motion is positive to the right and up is positive. That's just default. So we're saying up. So, okay. So in the y direction, I have normal up plus I get part of the force of pull up, FPY, we'll say. It's actually FP sine, because sine for the y, cosine for the x, sine of 30, minus, like you said, mg, and that all equals 0. So then the normal, you say to take the mg and subtract from that FP sine 30. So therefore normal equals 98, because it's 9.81 times 10. So we'll go 2 siggies, 98 newtons minus, we already said right here, 30. So the normal then is going to be 68 newtons. So that's the contact of the wagon with the pavement is 68 newtons. Even though the wagon weighs 98, only 68 newtons are in contact, because she's pulling up a little bit on the wagon. Okay. Hopefully that one made some sense, because now we're going to go to we're going to kick it up a notch, a little harder, and this is the last thing we'll do. And by the way, let's go ahead and do some more skipping here. Start to do a lot of skipping, and we start to do a lot of skipping in May. Skip, and we do have June as a backup, but still, I don't want to be doing this stuff in June. I'm saving the bigger ideas for June. So skip 5D, 5E. We're just doing what we need to do. Okay, so this time, first hour had a good idea. As we go along and do these, okay, we do circle and we label what it is. Well, that's mg. But let's also show the direction of the force. So mg, of course, is down. Okay. We're just kind of adding this. This will help us with our free body diagram, because they were having trouble kind of putting all the free body diagram. Snow contact produces a frictional force of 400 newtons. Remember that we're saying direction of motion is positive and to the right. That's default. Okay, this is the default. So on this one, then the frictional force then is opposing motion. It is sliding, and so that's F sub K, and it is 400, and it's to the left, and then he's pulling with a force of 750 newtons, but at 20 degrees above horizontal, so 20 degrees this way. Okay, so I'm just putting that to remind myself when I'm doing the free body diagram. What is Joe and the sled's acceleration? Okay, so I didn't include normal because it didn't really say anything about normal, but I know normal's there. So now I'll give you a minute to draw the free body. I think in class I went around and gave them an insta stamp on this one. They came around, if you draw the free body, if everybody did that and labeled it as I'm walking around, they got that insta stamp. That's another new feature. Wish there was ways I can give you guys insta stamps. Like put little stars by your name or something, you know? I don't know how they can do it on Zoom though. I mean, I give you Zoom points, but you'd have to turn your camera on. That's just not going to work. Okay. So you work, I work. Here we go. We're only going to do 5A together. What time we got? We got 10 minutes, and then I'm going to let you work on 5B, 5C on your own. Well, we'll work on that tomorrow, but let's just get 5A done. That's about as far as we got in class. Here's my XY axis. And we're saying that's plus. And that's plus. That's just default. Do 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 do. Black. All right, so we got 1800 newtons down. These free bodies are going to get more and more complicated, and they start to me, they start to become beautiful after a while. They're like works of art when you really get into it. The fine art of the free body. 1800 newtons, and there's a frictional force back of 400. Now the X forces should kind of be correct relative lengths to each other. The Y forces should be, but not X and Y. Don't try and, so X has its own scale, Y has its own scale. Anyway, there's my F sub K. And then we have this guy, 750, a little longer now, something like that. And I'm going to call that tension because he's pulling on a rope. So the tension here is 750. And of course, that's components of a right triangle. But hold on. We also have normal. Normal's not the same as MG. It's less because of that pull-up stuff. And maybe I don't need to worry about it, so let's not worry about it yet. And then we have this, let's put these together. Let's make this into a right triangle. We got the Y component and we got the X component. X. Okay, that's these are like little mini vectors. There's probably purists that wouldn't like me saying that, but like little components. They have direction. As we saw, as that was so critical with momentum that you had to give the direction of those. Okay. I'm kind of stalling here so you can catch up. It's nice to color when you stall. It releases serotonin or something because I feel better after I color. And that's 20 degrees.
Why is the normal force smaller than the mg?
Great question. Because this sled is not rising or falling, so all my forces in the y direction have to add up to 0. But notice that upwards you have both normal and this purple component of that right triangle, and down you only have mg. So n plus this ty is going to equal mg. So therefore n doesn't have to be as big as mg. See what I'm saying? So it's less in other words, the sled has less contact with the snow. And next week we are going to talk about London dispersion forces. So we are going to do more details on friction, the chemistry of friction next week. Okay, what is Joe and the sled's acceleration? So we're trying to find a sub x. So we go, we're down to 6 minutes here. We go fx. Pepper, you better not be peeing. MAX. Pepper, I can hear a little pause, but then she stops, and then I think she's daggone it. All right. Summation of. Because I have, okay, so, okay. To show our work here, let's go ahead and do the old cosine sine thing. So 750 cosine 20. That'll give me the orange part there. 750 cosine, make sure you're in degrees, cosine 20. 705. So that part is 705. And then 750 sine 20. Pepper, you better keep walking. 257. Uh-oh, that's purple. 257 newtons. Okay. I don't know. You know what? I don't know if I'm going to need that 257 newtons. I just did it because I had the calculator out. And I think that's a good idea. All right. So in the X, I'll do it in symbols, but I know I'm going to need those numbers in a second. So in the X, we have T cosine 20, which we know is 705, minus the force of friction. It's always minus the force of kinetic friction. Occasionally you add static, but that's a whole, we may get to that problem, but that may be a June thing. Equals MAX. I'm solving for AX. So AX, then we isolate that variable. T cosine 20 degrees minus FK over M. Now, if that were a test and you left it at that, you're going to get 7 out of 10 points. That's true on the AP. So AX equals 705 newtons minus 400 newtons divided by, not 1800. I'm not falling for that. 1800 newtons divided by 9.81. Because you got to pull the G out of that, right? You got to turn it into mass. A sub X then, I'm going to be lazy and go look at the answer. It's 1.7. A sub X is 1.7 meters per second squared. Okay. That's about how far we got. So I don't want to get too far ahead. We'll knock out B and C tomorrow. B and C are both orange, right? They're just orange kinematics. So this looks like it's second orange. And this will be first orange. And I think Pepper's doing something she shouldn't be doing back behind my back. Okay. I'll go ahead and do the screenshots and all this. And questions about what's going on in class?
Did you assign any more problems on the gold standard sheet today?
No, not yet. We assigned the front of 6.5 is your homework, except for those 2 we took out. And they're all like pretty quick problems. And you shouldn't spend more than 15 minutes. If you do, then I screwed up. Okay. Who's got questions? If there's no questions, you guys are free to go. Otherwise, stick around.
I have a question
Yeah.
about the test on the
Yeah.
26th. I have an AP test that same day and it's finals. Could I take it on the 25th?
You're being virtual. You can take it, you'll have a 2-day spread in there. We're talking about test 6B.
Yes.
Okay. I think you don't get that until you're being virtual. You'll get it the next day, but you have 26th, 27th. And I'm not requiring you, the virtual kids, to turn it in until the 28th, which technically you're not even in school. So
Okay.
you can turn that in 28th. Yeah, we can work. You have your own schedule there. You can work around it.
Okay. Thank you.
You bet, Rose. See you.